matter of reformatting and it wasn't ejected properly or
Here is the microphone. Cut it over here. Well, you don't have to do that.
You don't have to. You might be really hot, actually.
Here's the one video.
Yeah. And apologies for our high-end grocery equipment. This is low, $15 a piece.
Here's the one that.
Yeah. And it's Zico?
Yeah.
Do you mind being the camera calibration?
I have a really good shirt today.
Because your shirt is better than any other shirt for that. And so the focusing is by maximizing contrast. So this is why Zico is the perfect video game today.
I see. So this is better than a t-shirt. Just solid.
Yeah, I mean, t-shirt would be okay. What I'm doing is horrible. Yeah. Oh yeah. Yeah, actually.
They should be switched on, yeah. That's good, yeah.
No, it's okay. It's just. Oh. Oh, okay.
Who would you like?
Can you do it something?
No, there's
This
no
is
sound
not
from
here.
here. Speed.
No.
There's no
I
sound.
cannot hear anything. Well, because the cable's not plugged in. What?
I think it is.
Maybe we should. Yeah, you're running it. It comes in from the other receiver. Okay. No, that's the power cable. No, that's okay. What is another? No, we switched to a different receiver.
Each clarify your something about Everly Center and software feature side over that thing. Should she use it? It's fine.
How about the speaker? Does the sound check again?
Oh, yeah. Okay, check.
Yeah, that's where
how I'll speak when I speak for real.
Yeah.
Okay, we can talk later.
All right, we're happy to have Tom Mitchell again. Talk today about how the brain represents language. That would be the title. Before that, though, I want to again congratulate our current leaders on the leaderboard. Is anyone of these people here? Just all right. Well, congrats to you. And we have a prize for you if you want to come pick up, more. So, just what you wanted to share. Are you recording for that?
Yeah, I did. Should I? It's okay. Start another. Yeah. Oh, okay. Maybe start another one. Yeah, just wait until.
Conference organizers, I want to thank you for your advanced video setup. I can't remember the last time I didn't have to bring my own connector converter. Very cool. Well, good morning. My name is Tom Mitchell. I remember some of you from last Wednesday when we spoke about never-ending learning. And today I want to talk about something very different. And I know that you've been studying a variety of machine learning algorithms, and many of those talks that you've heard have brought up one application or another to kind of illustrate the utility of those algorithms and their capabilities. What I want to do today is kind of the other way around. I just want to tell about one particular application, which is one that I'm very interested in and working with some colleagues on for a number of years, which is to understand how the brain represents meaning of language, and in some sense, how the brain understands language. Those are the goals. And as a machine learning person, I've used this as a driving application, both because I care about it and because it turns out to be a pretty interesting application for machine learning too. So what I want to do today is just get you to think with me about the following question, actually questions. One is the science question about the brain, that is, how is it that the brain uses neural activity to represent meaning of the words that I'm speaking and that you're understanding right now? But the second companion question, given that we're in the machine learning summer school, is what are the roles that machine learning can play in studying the brain? And so those are the two questions I want you to help me think through today. So before I start, I should say this is really joint work with a number of people, including my primary faculty colleague, Marcel Just, who is a professor here in the psychology department. Marcel also happens to be the head of the fMRI Center, the Brain Imaging Center here at CMU. And he taught me most of what I know about brain imaging. And then a number of other people who've been involved. So much of what I'm going to talk about is really their work. Okay, so let's get on with the setting up the problem. So here's the brain teaser. Suppose you were interested in how the brain worked. Who isn't really? And suppose that you had some interesting instruments like this one. So this is an fMRI, functional MRI scanner. If somebody lies still in the scanner, then we can take pictures of neural activity. I'll show you some of those. And so we've been interested, given that we're interested in the question of how the brain processes language and represents meanings, what we've been doing for the last 10 years is putting people in scanners like this and showing them stimuli like these. Just simple things like words, like hammer. We'll put that on the screen for a few seconds, then we'll put a nothing on the screen or just a fixation point, then another word, and so forth. Sometimes we use pictures instead. Sometimes we use both pictures and words. As you'll see later, sometimes we use sentences, sometimes we use Harry Potter stories. But basically, we put you in a scanner, we get you to think about something, and then we get pictures of your brain activity, which look like this. This looks like 4 pictures, but it's actually part of one 3-dimensional picture of brain activity. The top of the picture here is the back of the head, posterior. Bottom of the picture is the front of the head. And these are 4 different horizontal slices of what's really a three-dimensional picture of brain activity. With fMRI, we get almost 1 millimeter spatial resolution in where the neural activity is. And as this little thermometer on the side indicates, red here means high brain activity. Green means typical brain activity. That is the same level of brain activity that we see when we don't show you a word, we just show you that fixation. And blue means actually suppressed brain activity, even less than we see when you're even less than we see when you're looking at the fixation point. And there is really no blue here. So this little hole in the brain is really just white matter. We're only interested in cortex, the gray matter in the brain, the part that actually has synaptic neural activity. Okay, so what you see here is actually brain activity from one person when they looked at this particular stimulus. It's the word bottle with a picture of a line drawing in the bottle above it. Okay, so the brain teaser is if you had access to a toy like this, I'm sorry, an instrument like this, and you were curious about how the brain worked, and you knew the machine learning algorithms that you know today, then how would you study that question? So before we get on to that, let me just show you a little bit more data. So as you can see, this person has blotchy neural activity, especially in the back half of their brain when they think about the stimulus bottle. But you could ask me, well, what does it look like when they think about, is it any different from when they think about any other word? So let me show you the mean average activity in the brain averaged over 60 different word stimuli for this same person. And that looks like this. Okay, so the typical word causes also blotchy activity, mostly in the back half of the brain. But if you squint, you might see some differences between the activity for a bottle and the mean activity averaged over several words. In fact, I can subtract out this mean activity from bottle and show you the difference. And in fact, for a lot of the machine learning algorithms that we run, we work on this version of the data. That is, we subtract out the average over a lot of different stimuli. And that allows us to look at just, allows our algorithms to look just at the difference between the activity for this stimulus and the average activity. Okay, so if you look at it and see, well, maybe there are some differences there. Maybe it's noise, maybe it's signal. How would we know? All right, so if you're a machine learning person and you are faced with this, probably one of the first things you'll think of doing is why don't we try to train a classifier to decode from the neural activity that we observe which of several possible classes of stimuli the person is looking at, right? And you know lots of classifiers. We might use logistic regression, support vector machines, decision trees, you name it. And in fact, we've tried this, and it works quite well. So we can train classifiers. In fact, we found that probably our two favorites at the moment are logistic regression and support vector machines. They tend to work as well or better than other things that we've tried. And we've also kind of learned that we have to do, for example, significant feature selection on this. There are roughly 20,000 different three-dimensional points in that image. We call them voxels instead of pixels because they're volume elements. So there are about 20,000 voxels in one three-dimensional image. And it turns out that only 1 to 10% of those are relevant to figuring out what the semantic content of the stimulus is. So we've also learned that we have to do some kind of automatic feature selection, either with L1 regularization. Did you guys talk about that? Or by doing some more explicit cross-validation scheme where we pulled out some data, experiment with leaving out different features and see what works best on the cross-validated side. Okay, but when you do this, it turns out it works quite well. So for example, this shows the accuracy on a held-out set of test data, cross-validated, of a classifier trained in this case for telling whether the person's thinking about is looking at a stimulus that is some kind of tool like hammer, screwdriver, chisel, or some kind of building like apartment, palace, house. And what you see here is for each of several different people, participants in the study, how accurately the classifier can decode which of these two categories, tool or building, the person is thinking about. So that's kind of interesting. For some of these people, we can get nearly perfect classification accuracy. For other people, not so well. You might ask, and by the way, for just about every experiment that we run on several people, we get this kind of a profile of accuracies. And it turns out that the more accurate people hold their head more still in the scanner, the less accurate people are the ones for which we measure more wiggling of their head during the experiment. So it's probably a signal to noise issue. Okay, so you get the idea. It turns out that despite the fact that this machine gives us a fairly noisy signal, we can classify, to some degree, the mental state of the person by training a classifier that looks at these 20,000 points of neural activity and determines, are they thinking about a tool or a building? Which is something we didn't know when we started this. We didn't know whether the brain would, neural activity we observed would have enough resolution to distinguish which thing you're thinking about. So at least for concrete nouns, nouns that describe things you can touch, like a glass, or a building, or a tool, this works fine. Okay, so now once you have this tool, the ability to train classifiers, you can use it actually to ask a lot of interesting questions. Right? So like one question we could ask is, are these patterns of neural activity that the classifier is learning the same in your brain and mine? Or do we have different hash codes that each brain is using? So we asked that question, are neural representations similar across people? But to study it, we can actually convert that into a machine learning question. What would be the machine learning question? What machine learning experiment would you run to answer this question? Maybe this is, okay. Here's what I would do. I'd say, let's train a classifier using the brains on this side of the room. And once we've trained it, we'll use it to try to decode what stimuli the people on this side of the room are thinking about. And if that classifier succeeds, then obviously the patterns of neural activity over on this side of the room are quite similar to the patterns of neural activity on this side. Okay. So we tried this, and what do you think the answer is? Very interesting. So here you see again in black what happened, what kind of accuracy we get for each participant if we train and test just on data from their one brain. And here you see in white what happens if we test on their brain, but we train using none of the data from their brain. Instead, we train using all of the data from all the other people in the study. So this is pretty interesting. The white bars on average are about as high as the black bars. That means that on average, we can do just as well decoding what you're thinking if we train on everybody else as if we train on you. It's also a little scary for some of these people that we can do better if we train on other people than on them. Any idea why that might be?
Noise reduction.
What's that?
Noise reduction.
Noise reduction. That's right. So these could be the noisy people, the people who move a lot. So the training data is going to be noisy, but so will the test data. This bar shows that we're getting this accuracy classifying data from their brain, although we did not train on their brain. So the noise is still with us.
Just a very naive question. Don't you have two confounding effects here? Variate shift and sample size?
So what are the two?
Variate shift and sample size?
Yes. Good, good. So Alex, of course, got it. That's why he's in charge here.
No, you should have seen this picture last week, that's the point. I had the same picture there.
Oh, really? Okay.
Yeah, for emails.
Oh, okay. So there is a confound, which is this classifier was trained on the data from everybody else. So it had 1, 2, 3, 4, 5, 6, 7, 8 times as much data, 8 times as many training examples that it used than the classifier that was trained only on the data from this one person. So one possible explanation there is, of course, the more data you train on, the better you're going to do. But still, nevertheless, the important point here, scientifically in terms of brain science, is that, wow, this is very compelling evidence that you and I have very similar patterns of neural activity that encode the meaning of different things we think about. Even though we're all different, granted, we all grew up in different houses, have different life experiences, but this is the fact. In fact, this is a very robust result. Yes?
Are the results gathered from just optics, not, I should say, like subjective meanings, like something more creative, like their brain activity when reading something, like I don't know.
So you're talking about the range of stimuli that we used in the study. These were all single words, concrete nouns describing concrete objects. So very uniform, homogeneous domain. We picked this because we thought it would be simple. Yep.
Only visual input?
Only visual input. In this case, it was line drawings with a word written under it, like that first example. We've tried auditory input too. It's a little hard to do auditory input in the fMRI scanner. If you've ever been in an MRI scanner, you're familiar with the idea that they make a lot of noise because they're switching magnets on and off, and that makes this big clunking noise. So if you use auditory input, you have to time it so that it's not blurred out by the hammering of the machine. Yes?
Does it not just say that it is a visual interpretation of the brain, which is same for everyone, than what they think about the object?
Ah, good, good, good. I like this question. So if you didn't hear it, the question was, how do we know this is the neural activity that's capturing the semantics, the meaning of the word, instead of the neural activity that's capturing the fact that this is a H-A-M-M-E-R. It's just the visual percept of the letters, for example. That's a very good question. And we got interested in that question too. And we converted it into a machine learning question in a similar way, right? So we could ask, yeah, so we did it this way. So we also asked, well, what if we present the stimulus in different languages? Or we'll present it sometimes as a word and sometimes as a picture. And in that way, we know that if, and so for example, for language, we got people who are bilingual, Portuguese, English. We presented half the stimuli in Portuguese and half in English. Then we trained a classifier using only the Portuguese word stimuli data. And then we tested whether it could successfully decode the neural activity when people looked instead at the English words. And it was just as accurate either way. Similarly, we did a picture, a study where once, for half of the stimuli, we presented just line drawings, for the other half, just the characters string. And again, we found that we could train on one and decode the other. And so based on that, we conclude that the neural activity that the classifier is picking up on, in fact, has to do with the meaning, the semantics of the stimulus, not some low-level perception. Although this is such a fundamental question, and we'll be back to it later, but probably the truth is we're seeing both types of neural activity. And so, in a way, you should keep that in mind as you're interpreting any of these results. In fact, the first result that I presented, where it was either tool words or building words, already has built into that a little bit of a safeguard about this question, because we weren't training for individual words, we were training for a category of words about tools, hammer, chisel, and those have very different visual percepts associated with them. So even classifying semantic categories of stimuli as opposed to individual stimuli is one way of trying to deconflate these two issues. Yes?
You have anything where you pre-train the fellows and say, you know, if I give you a poke on a leg, you think about a hammer or something like that?
Ah. No, we did not do that. Although, I'll tell you, we did a very, well, we did the following thing, which we're currently writing up. A couple of years ago, about a year and a half ago, David Pogue, who is then a New York Times tech writer, since then he's moved to Yahoo. And he was also running a show, Nova public television show that he was producing about the brain. So he came around to interview us about this work. And as part of the interview, we put him in the scanner. We showed him some of these stimuli. We captured his brain images. We showed that our program could successfully decode the images, and we videoed the whole thing. It all turned out well, so we were happy. We're eating lunch, and David says to us during lunch, you know, I'm actually an amateur magician on the side, and what you just did to me would not hold up to a magician's scrutiny. Because here's what you did. You had a computer show me stimuli, you captured my brain images, and then you had that same computer tell me what the stimuli were. Not very compelling. So we insisted that we're honest folk, but okay, so during lunch he convinced us that after lunch we should do one more thing, which is that we'll give him 2 words to think about. And so we picked words that were very different. We gave him the words skyscraper and strawberry. And he would then go in the scanner, and we would show him every once in a while a dot, just a dot on the screen. And when he saw a dot, he would pick one of these words and think about it. And he took a little piece of paper in the scanner with him. And so when he came out of the scanner, we had shown him 10 dots. And he had 10 little marks on the paper, which he was not showing us. And then the program had to decode. So this was kind of interesting because now there are no perceptual cues at all. It's just the same dot each time. It's just a totally internal volitional creation of a thought that he was doing. And the program was 10 out of 10. Telling which of these words he had done. It turned out that was the first time we ever ran an experiment where we did not have a different stimulus on the screen as you're thinking about different things. So based on that thing that he got us to try, we're actually, now we've done that as a more careful study on a number of people, and the results are are very clear that you can do this even if people are internally generating thoughts, which is an interesting thing scientifically, because there could be questions about if you perceive something and think about it, is it the same as when you internally generate it? And clinically, it could be pretty interesting. There are some people who are called locked in who don't have muscle control to speak, for example. And so if there's a way to use this kind of approach to help them communicate, that would be very interesting as well. Okay, so I want to move beyond classifiers, but just to summarize, I think of these classifiers as effectively in the following way in terms of the field of brain imaging. Brain imaging devices are wonderful because now, for the first time in history, we can look and see neural activity in the brain. But what classifiers do is they let us do something different. They let us look and see what is the information content in the brain, instead of just what the neural activity is. Right? We can decode whether you're thinking about A or B, in addition to seeing where's the neural activity. So just like brain imaging devices caused a kind of revolution in the field because for the first time you could see neural activity, classifiers, in a way, have now taken over, in the past decade, the field of brain imaging. Well, maybe taken over is too strong a statement. They now play a major role in publications, research going on in the brain, because they allow us not just to look at where the neural activity is, but also where the information is encoded within that neural activity, and what information is encoded where in the brain. So just to make that point, before we leave classifiers, here's an idea originally due to Nico Kriegskort, who, once people started using classifiers to decode brain images, Nico said, well, why don't we just only give the classifier a very small fraction of neural activity and see whether it can decode it from, say, the left side of the brain, or from the right side of the brain, or from the front half of the brain, or from the back half of the brain. In fact, what Nico suggested, and what this picture shows, is what if you train a classifier on 1 cubic centimeter of brain tissue, and you move that cubic centimeter around in the brain to every possible location. And in this case, we're back to tools versus building. This is the classification problem here. And what this picture shows is the accuracy of a classifier trained on a little 1 cubic centimeter of brain tissue as you move that classifier around in the brain. And what you see here is that in most places in the brain, we cannot accurately decode the difference between when you're thinking about tools and buildings. But in a small number of places, in fact, we can get quite reasonable accuracy, 70 to 80%, using just this little cubic centimeter. So in a sense, that's a sense in which the classifier is really a little virtual instrument that you can use to probe here, here, here. What is the information content in this location of the brain that's encoded by the neural activity? It's also quite interesting. This is a classifier for distinguishing whether you're thinking about tools or buildings. Guess what these parts of the brain are? This part is part of motor cortex. Motor cortex is the part of your brain that's active if you plan to do this or this. For example, use a tool. And that's one of the places where we can distinguish whether you're thinking about tools or buildings. In fact, as soon as I said to you hammer, I generated neural activity in your premotor cortex. We see that in everybody. That's part of how your brain encodes it. What do you think this part of the brain is? It's a part of the brain called the parahippocampal gyrus. But what's important about it is previously other studies had shown that this is the part of the brain that activates when you think about your spatial location relative to other things. So if you think about your location relative to me or the ceiling and the walls and the floors, you're going to generate activity in that part of your brain. And when I say to you the word apartment or house or palace, I generate neural activity in that part of your brain. So using these classifiers and seeing where the information is coded that distinguishes, that discriminates these different categories of words, we can start to see, for example, one of the big surprise results is that many of these neural representations for concrete nouns are actually grounded in the sensory motor regions of the brain where that would be activated if you actually interacted with that object instead of just saw the word on the screen. If I say to you the word apricot, I just generated activity in gustatory cortex, the part of your brain that's active from a sense of taste. It's part of what it means for you to think about apricot is to generate activity there. Obviously, you're not tasting. You weren't consciously aware of tasting an apricot when I said it to you, but we know that it generates that activity. So that somehow the way your brain encodes these things is tied to the way that it perceives and controls them. Okay, so just to finish up this, somebody did ask earlier, what about other stimuli? And we did try this on other kinds of words. It turns out the easiest to decode are these concrete nouns, but also words about emotions. If we give you words like anxiety and love and hate, we can distinguish which of those words you're thinking about, at least as accurately as the concrete nouns. On the other hand, if we give you words like justice and democracy and machine learning, it's harder to distinguish. And if we give you verbs in isolation, this was one of our biggest failures. So when we started, we tried these nouns and it worked so well, and we said, oh, let's just do verbs. So we gave people stimuli like cut or heal as verbs. And we found we couldn't even train a classifier to do better than chance, distinguishing which of those verbs you're thinking. But later, a couple of years later, we found out that we could distinguish whether we gave you the two-word sentence, doctors cut or doctors heal. That works fine. But if we give you just the verb cut and the verb heal, we don't get stable, repeatable neural activity. So that's kind of interesting too. I'm not sure what it means, but these are some of the things that we're finding. Yes?
Did you look at if the verbs were associated with an object itself? Like if you think of cut, you think of scissors, something like that?
Oh, you mean like hammer?
Just like if you show the word cut to somebody, instead of just generating activity for cut, they generate activity for scissors or something like that.
I see.
So they associate it with something, with a default in the object.
Yeah, I don't know. I see what you're saying. You're saying if I show you an object, do you think of a verb?
Or
So
the other way around.
Or the other way around. I'm not sure quite how to study that question.
Maybe if you train with tools, with object tools, and you show me verbs, see if when I think of a verb, my brain responds.
Right, so then if you show the verb, do you see something like one of the tools or a fragment of one of the tools? We could do that. We have not done that study. The fact that you had to give a noun with the verb in order to get a repeatable pattern makes it a little trickier. Okay, so I want to move on because everything I've talked about so far is how we can use classifiers to decode brain activity. It's very valuable. It's probably the single most interesting use of machine learning in studying brain image data. Single most widely used idea. There are hundreds of papers now, journal papers published that use these kind of techniques to do this. But if you're interested in developing a theory of how the brain represents meaning, then having a set of classifiers, say one for each word, is not a very satisfying theory. Right? But I can give you classifiers for 100 or a couple hundred words in English that capture the patterns of neural activity. But if I claim that was a theory of how the brain represents meaning, you wouldn't accept it, right? You'd say, no, that's just a list of patterns of neural activity for different words. Where's your theory? And theories, of course, are logical systems that make predictions, hopefully testable predictions that can then be tested by experiment to validate the theory. So we got interested in the question of what would it mean to have a theory of neural representations? And one aspect of that would be, if we had a theory, it would be nice if it could take an arbitrary noun and predict for us what would be the neural activity pattern for that noun, even if we hadn't yet collected any data about that noun. So then would be a more expansive system. So we thought about this for a while, and then we came up with a way of training a machine learning system to do this. And it looks like this. So this trained computer program predicts for any input noun that you give it, predicts the neural activity that we'll see when we actually show it to a person. It doesn't predict it perfectly, but as you'll see, it predicts it quite well. But it predicts it in a two-step process. The first step is it takes the word that you give it, like telephone, and it looks it up in 1 trillion words of text provided by Google from the web. And it represents that word by corpus statistics drawn from the text. Statistics like, how often does telephone occur with the verb walk, or eat, or ring, or whatever. And then given that feature vector character approximation to the semantics of the word, it predicts the neural activity at each of these 20,000 locations in the brain as a function of that feature vector. So the key here is, if you want a computer model that can take any word, then you need some canonical representation scheme for taking any word and turning it into a kind of standard representation from which the program can manipulate it. And in our case, that standard representation comes from looking up the corpus statistics of the word on the web. So let's look at that in a little more detail. Here, in the first version of this program, the corpus statistics features that we used were 25 verbs that I just made up. But I made them up based on this observation that many of the concrete noun representations were based on sensory motor regions of the brain. So I picked verbs that had a lot to do with sensing and motor actions. And then when you, for example, for a word like celery, here are the features we get from the text. And so you could see, for example, celery occurs a lot with the verb eat and taste, but it doesn't occur very much with ride. Whereas airplane occurs a lot with ride, but not very much with rub and taste and manipulate. So these are the corpus statistics for these concrete nouns that we get. That's step one in this model. And then step two, once we have brain images for a set of nouns, and we have these representations of their approximations to their meaning in terms of corpus statistics, then we run a very large regression we learn a function from these feature vectors to the activity in each of the 20,000 places in the brain using regularized linear regression. And to be precise, we predict the model that's trained predicts the activity in voxel V, like this voxel right here, for example, as the sum over these 25 verb features of how frequently the ith verb occurs with the input stimulus word W, times some coefficient that the program has to learn. And this coefficient relates the frequency of verb I to voxel V, tells how much that verb's influence is on voxel V. And so when you put it all together, you have, for example, the prediction for celery. Well, we just saw the corpus statistics for celery said that it occurs 0.84 with eat. And so we'll take this set of learned coefficients. This is not a plot of brain activity anymore. This is now a plot of the learned coefficients in the model. But for example, to predict this location's activity, we'll take 0.84 times the value of this learned coefficient for eat, plus 0.35 times this coefficient for taste, plus 0.3, you get the idea. Add those all up as a weighted linear combination, and that'll be our prediction for the activity in that location for the word celery. Right? So we're predicting the activity for an arbitrary noun by going through this intermediate set of features which happen to be verb co-occurrences. So the model is trained only on nouns, like we trained it on a set of nouns and their observed brain images. We end up learning 500,000 of these different coefficients. And you see pictures of a number of them there. Does that make sense? So that's the model. And so you see machine learning kind of at work here, but now it's in a different framework. And it's for a different purpose. Yeah?
In that dictionary collection, did you separate out the nouns from the verbs?
No, actually, we just, the Google data, which you can download from the web, is what they call their n-grams data. What they did is they took 1 trillion words of text from the web, and they created files that you can download. They have every n-gram. An n-gram is just a sequence of n words. And they do this for n up to 5. They have all sequences up to sequences of length 5. And they'll show you what the sequence is, like the speaker drank the water. And then they'll tell you the frequency, how often that occurred in this trillion words. That's the data. And so we didn't do anything tricky. In fact, we weren't even distinguishing whether something was the object or the subject of the verb eat, whether it was getting eaten or doing eating. We just looked at co-occurrence of the tokens. Subsequently, we found out we can do even better if we actually do a dependency parse of the text. And so, as you'll see in a sec, we have better results. Okay, so that's the basic idea. And but what it does is it gives us now the ability to use this model to predict neural activity for words that we haven't yet seen. And what I'm showing you here is what happens if we train the model on 58 words, nouns, not including celery or airplane, and then we force the model to make the prediction shown on top for celery and airplane. And unknown to the program here are actually the observed fMRI images for celery and airplane. So if you look at these, you can see they're not perfect, but they're capturing some of the interesting structure that's actually in the neural activity. Okay, so now we can One way I can show you how well it works is to show you pictures like this. A better, more quantitative way would be to set this up as a decision that the program has to make. So for example, what we can do is I can leave out 2 words during training, like celery and airplane, then give the trained model those 2 words, celery and airplane, have it make its predictions. Then I show it the 2 actual images, but I don't tell it which one is celery and which one is airplane. It has to tell me. And of course, if it was just guessing at random, it would get half of those right by chance. And if I worry about statistical significance, it would be statistically significant if it gets at least 61% of those right. So when we tried this, averaged over 9 people, the program got 0.79 of those rates, 79%. So that means 3 times out of 4, we could give it 2 words it had never seen, and it was able to predict the neural encoding for those words well enough that it could tell us which of the brain images was word A versus word B. So it's an interesting machine learning model because it lets us extrapolate beyond the words that were actually in the training data. And why does it do that? Because it's able to go through this intermediate feature vector encoding of arbitrary words. And we can train, with respect to that feature vector encoding, train the model, and then we can take any word we can think of, look up its feature vector encoding, look up its corpus statistics, and then get a prediction for that. I have to make a little decision here about what to cover and not. So, so that's the model. So you see how machine learning, again, kind of comes to the fore in making it possible to do this. But then, if you think carefully about what's going on here, you say, well, what are the assumptions that are implicit? We're claiming that we're developing a general model that can predict how brains encode meaning. It's a fairly fundamental thing. What are the assumptions in here? Well, in this model, there are 2 basic assumptions. One is that the usage statistics of words on the World Wide Web are sufficient to predict the neural activity in your brain when you think about a word. That's pretty interesting. The second assumption that's in here is that somehow these 25 features, those 25 verbs that I happen to pick, and I tried about 10 sets. I didn't try, it wasn't the first one I picked, but I didn't try hundreds. It just kind of messed around. Another assumption here is that those 25 verbs and that 25-dimensional vector space characterizes everything, every concrete noun you could ever think of. And that it lives inside this 25-dimensional vector space. So that's kind of a big leap. And it probably isn't true that those are the 25 dimensions precisely that the brain uses. So that led us to think about the question of, well, what are really the semantic primitives that the brain is using to assemble these patterns of neural activity? We happen to have chosen one that worked okay, but maybe there's a better one out there. So we started experimenting with alternative feature vectors. Instead of 25 verbs, what if we use more verbs? Well, we tried it, didn't help. What if we use all the 50,000 most frequent words in English? That didn't help. In fact, it made things worse, despite the fact that it includes those 25 verbs. Why? Probably because our machine learning algorithms weren't good enough to make up for the many irrelevant features in those 50,000. We tried something called lake semantic analysis. That didn't work. Fernando Pereira told us we should try this great feature vector set from Colbert and Weston. We tried it. So we were kind of stuck, and then one day, Dean Pomerleau, colleague of ours, came in and he said, try these features. And he gave us 218 features that he collected from Amazon's Mechanical Turk service. And he had given our words in 218 questions and got people to answer these questions. So you give them a word like celery. Is it heathery? Is it flat? Is it curved? Is it colorful? Is it hollow? Can it break? Can it swim? Can it change? And so forth. People would answer these questions for those words. And he said, use these features instead of the verb statistics. And that helped. So that was kind of interesting. Then more recently, Brian Murphy and Partha Talukdar collected feature vectors of size 100 million by using a dependency parse of 500 million web pages, of every sentence found on 500 million web pages. This is like tens of billions of sentences, roughly 10 billion sentences. And so now the features are things like, for example, for mango, it's the subject of the verb grows, it's the object of the verb eat, and so forth. And that actually works pretty well. 100 million is a very high dimension for the vectors, so we run principal components analysis on that to shrink it down to only 800 dimensions, and then it's manageable. But that boosts our accuracy. So. But then the most interesting thing, and the thing that I'm proudest of, is that machine learning came in and saved the day. You could think of this as a learning problem. Instead of generating and testing these alternative features, what if we set it up as a machine learning question? What are the best features? And have the program learn that. And that's what Indra Rastandi did for his PhD thesis. And he found 20 features that outperform all of the ones we have so far. And he did it by setting it up as a machine learning problem. So how would you do that? Well, there are a couple ways, but here's the way he did it. He trained the model by first, he had 20 data sets from 20 people. Half the people saw 60 concrete nouns presented as words only. The other 11 people saw them as words only. 9 people saw them as words and pictures, but they were the same stimuli. So it's like bottle either as a word or as a word plus a line drawing. He took this and he ran a program called canonical correlation analysis. Have you guys talked about that this week? No? Okay. Have you talked about principal components analysis?
Yes.
Have you talked about any algorithm of the form wildcard CA, PCA, ICA, CCA? So you did talk about principal components analysis, and you know that that's a way of taking some high-dimensional data and squeezing it down to a lower dimensional feature vector. Canonical correlation analysis is a beautiful algorithm that does something like that, but it's way cooler. Because it can take several different data sets, the data from 20 different people, and it can find a single smaller dimensional representation that you can map all 20 of these data sets into. So that you should end up with a data set independent feature vector that all of them can map into. How does it do this? Well, the reason it's called canonical correlation analysis is that what it does is one feature at a time, it learns, say, the first feature by finding 20 linear mappings, one from each data set, such that those linear mappings produce one feature that, where those 20 features that are produced are maximally correlated across the different stimuli in the data set. So let me show you more precisely what I mean by that. Canonical correlation analysis. Given data sets A and B, so A and B, for example, could be 60 different brain images from you and 60 different brain images from me for the same 60 stimuli. Those could be the two data sets A and B. It will learn linear functions F1 and F2, a linear function for your brain and a linear function for my brain, such that the output of those linear functions, when we give them, in turn, each of these 60 brain images, then we'll get 60 outputs for your brain, and we'll get, for my 60 brain images, we'll get 60 scalars, 60 single numbers for my brain. And it will learn the parameters of these two linear functions, your brain's and my brain's linear functions, in order to maximize the correlation in those 60 outputs of your brain. It'll maximize the correlation of the 60 outputs from your brain to the 60 of mine. And that'll give it the first feature of the vector. Then it'll subtract out the influence of that and repeat the process to get a second feature. So in the end, what it does is if we have a data set where each row, each brain image is some featured vector, a brain image, it'll learn a linear mapping that, or several linear mappings that produce a vector as an output for each input vector, and similarly for data set B, and those two will be maximally correlated. If you think better in terms of matrices, then you can think of it this way. We're given your brain data, which each column here is a brain image. So in this case, we have 5 brain images from you, 5 brain images from me. Notice your brain is bigger than mine, because it's not necessary that all the data have the same number of features. You can have more voxels in your brain than I have. That's fine, no problem. And then what's learned are these weights, W, one for you and one for me, so that when we apply that weighting to the voxels in each column, we get these 5 outputs for the 5 brain images of me and the 5 for the brain images of you. And WX and WY are learned in a way that optimizes or maximizes the correlation between these outputs and these outputs. So it's really a beautiful way of registering the two data sets, A and B, X and Y, registering those, but instead of doing it in the original data space, we end up registering them in this synthesized, discovered latent space. For brain imaging analysis, this is very important because we all do have different sizes and shapes in our brain. And one of the problems I didn't bother to discuss, and fortunately nobody brought it up, is that my brain is not the same size and shape as yours. So if I train on my brain, how is it that I decode your brain? The answer is we use some not very smart morphing algorithms that spatially warp your brain and mine into a canonical brain. But yuck, that doesn't work very well. And this is much more elegant and effective way of doing things.
How do you pick the number of latent variables?
How do you pick the number of latent variables? Very similar to the PCA question. So the first variable that you get is the one that dominates. Then the second one is slightly less effective, but still helps. And there's a kind of diminishing returns. What we do is we use cross-validation to decide where to stop this. And what do we cross-validate on? Well, it depends on what we're trying to use this latent representation for. Which brings me back to Indra's work, because what I just described is just the first step. this is how, so he uses the CCA method to discover a latent representation where effectively these 20 features, actually they allow you to look at somebody's brain image, map it into this person-independent 20-dimensional space, and then if you like, you can map it back down to predict what this other person's brain image will be. So this is the person-independent latent representation. Now, what are we using this for in this case? Remember, we want to train a model that will predict this brain activity for arbitrary words. So the second step in Indra's approach is to go ahead and train some model that will take in an arbitrary word, encode it using one of our standard ways. In this case, he used those 218 mechanical Turk features. Then he trained a regression that would predict these 20 CCA components from the mechanical Turk features, from the given features for any stimulus ring. And so now he's predicting what those 20 features will be. And then from there, you want to predict these. Oops, but we've learned linear projections from here to here. So as a final step, we have to invert those, or actually pseudo-invert those, so that now, given a word, we can predict each of the 20 components of the person-independent brain activity, and then in a person-by-person specific way, predict their individual brain activity. So I really like this model for a couple reasons. One, it lets me talk about the wonderfulness of CCA. But number two, unlike the first model that we trained, this one gets to train simultaneously on the data from all of our subjects. In fact, also from 2 different studies that we did, one of which used words only, one of which used words and pictures. And I think this is the style of model that's going to be increasingly popular in the future for brain imaging studies. Why? Because even though brain images are big, they have 20,000 pixels in them, we're still data starved in terms of, if you think about the machine learning problem of learning how something as complicated as the brain is operating, and we have data from 60 words and 10 people, that's not very much data to learn. Your brain has, 10 to the 10th neurons with 10 to the 5th connections for each one of them. There are a lot of things in there. And so we're fundamentally data starved in, for many experiments that we have. What I like about this model is that it lets us bring together data from multiple people, multiple experiments to train a single model. And I think you'll see more and more of this kind of machine learning research impacting brain science as we go forward, as the field matures, and as people start noticing that there's a lot to be gained if we can only come up with machine learning algorithms that can simultaneously take in data from multiple people, multiple experiments. So that's actually an open challenge problem. There's some great thesis topics in there, right? So, for example, we have on our disk drives probably easily over 1,000 brain image data sets collected from different studies on different people, sometimes presenting Portuguese words, sometimes English, sometimes pictures, different words, sometimes verbs, sometimes nouns, sometimes other things. We're not smart enough yet to know how to build a machine learning algorithm that takes into account all that training data at once and gives us the most constrained computational model of what's going on, what is the systematicity in this data. Instead, we're still reduced to looking at a small number of data sets at a time. But if we could come up with machine learning algorithms that could absorb, suck in all this experimental data that we already have, it's just of diverse types, slightly different experiments, we don't know how to munge it all together. If we could, it would be a revolution in the field. So I think that's an interesting direction for this crowd to be thinking in, because you could really make an impact. And brain imaging is just one of many scientific fields that I think have this character. Much of empirical science, whether it's cell biology or brain imaging or astronomy, cosmology, still is in this regime where we use function approximation algorithms. And so we need data to be all of a certain type, and yet the field has very diverse experimental data. And as machine learning researchers, we haven't lived up to the potential of actually providing algorithms that can simultaneously take into account all that data. So I think there's a big space of very interesting research to be done in support of empirical sciences, where the one-sentence summary is build algorithms that can really use the diversity of data that's available, instead of algorithms that require just a single, very strict, straitjacketed regime of data. Okay, so let me take another 15 minutes to change around the story. Let me spend a few minutes on this one idea. This is another thing that, like CCA, leads to an algorithm that might be relevant to you, a different algorithm. So, so far we've talked about this model that we provide a word and it would predict the brain activity. But Mark Palatucci, one of our PhD students, said, no, I want to train the model in the other direction. I want to give it any brain image, and I want it to tell me whatever that person is thinking about. What's the noun closest to whatever this neural activity is? So basically, he just trained the model in the other direction. So what would that mean? That means if we have a model with, let's go back to our 25 verbs, just to keep this simple. That means he wants to train something that looks at the brain activation and predicts the values of each of those 25 verb features. And then he had a big dictionary, we have a big dictionary, I'd be happy to share it with you, of the 50,000 most frequent words in English and what their verb co-occurrence statistics are. So his model was pretty simple. He just trained a big regression model to predict these 25 features from whatever the brain image is. And then he did a kind of nearest neighbor. Given the feature vector that got predicted, which of the 50,000 words in English has the most similar feature vector? And he matched it to that and said, okay, here's the word this person's thinking about. And when he tried this, it worked quite well. For example, when he trained on data that did not include the word bear or dog, then he could predict, oops, I see. He was not doing the 25 verb features. He was doing those 218 mechanical Turk features. That's what he was predicting. But here you see in light, brown and blue, the model predictions for, say, the word dog. This is predicted, and the actual answer is to, does it provide protection? So given the brain image, when somebody is thinking about dog, even though the model had not trained on that, it predicted that, oh yeah, from that neural activity, yes, it's thinking about some object that does provide protection with this strength. The actual mechanical Turk people gave it this strength. But for bear, it predicted, yes, bears also provide protection a little bit, whereas mechanical Turk people predict, no, bears do not provide protection. Is it wild? Does it stand on two legs? Do you love it? You get the idea. So there's a different regression for predicting each of these features. By the time you combine all 218 features, then you can see that you're going to be able to distinguish bear from dog pretty well, even if you don't get every one of them perfectly right. So he did this, and then he tested it by giving the program 1,000 candidate words. So here's a brain image. Here are 1,000. He took the 1,000 most frequent words in English. So you could be thinking of any of these 1,000 words. He left out the 59 training words. So there were actually 941 candidate words. And then what he found was that after training, when he gave it the brain image for a new word that had not been trained on, and he asked the system to predict to rank order these 1,000 candidate words from being the most likely to the least likely word they were thinking about, that the rank of the correct word in the program's ranked list was at the 92nd percentile. So it didn't always get exactly the right word out of 1,000, but it was in the top 10%. And the mistakes are also very interesting. So for example, for the word bear, it actually got it number 1, it predicted bear. Its second choice was fox and wolf. Similarly, foot, screwdriver, training for truck, it was wrong, it predicted jeep. And then its second choice was truck, and the third was minivan. For celery, its first choice was beef and artichoke. So even the mistakes are actually quite reasonable, right? They're semantically reasonable. All right, now why did I want to bring this up to you? Well, this is an algorithm that Mark called zero-shot learning, because one way to think about this algorithm, and maybe it's relevant to the software project, one way to think about this algorithm is it's a way of doing classification where you have thousands of classes. In our case, the thousands of classes are the words in English. And you have training data not for every class. You only have training data for a subset of those classes. The classification problem here is, given a brain image, which of the 50,000 classes in English, of English words, is this person thinking about? That's the classification problem with 50,000 candidate labels. But we have training data, in this case, only for 60 of those 50,000 labels. And yet, as you can see here, these are extrapolating beyond the training data. These class labels, like celery, were pretty well dealt with, even though there were 0 training examples for that class label. So the algorithm in general, even though we happen to apply it to brain image data here, is actually a useful algorithm that people have also used for computer vision, for example. If you have thousands of labels and training data only for a subset of those, you can still build a model, train a model that will predict any of the class labels, if you set it up with some intermediate feature vector coding of the class labels. That's what he's doing here. He's coding each class label with these 218, a vector of these 218 features. Right? Will it protect you? Do you love it? Is it wild? And lots of others. And so the key is, even though you don't have data for every class label, you do have data for each of these 218 features in the vector encoding of the class label. So people have done very similar things in the computer vision community, where you have an image and you're trying to classify what are the objects in this image. And there might be thousands of possible objects. Or what type of scene is this? And maybe you haven't seen exactly an object like in 2001 Audi TT Coupe. But if you know that there are a couple hundred features that your class labels can fit into, like, is it a vehicle? Does it have tires? Is it outdoors? Do you love it? Can it protect you? Then, just like we could train a model from the brain image to this feature vector and then do a nearest neighbor match to see which class label we thought it was, you do the same thing in computer vision. And I took a glance at the software project you folks are working on. I saw the leaderboard right before we started. And I saw that there were a lot of class labels. I didn't get into the details of it, but maybe this zero-shot learning, now you see why it's called zero-shot learning. You can learn to classify labels for which you have 0 training examples. Maybe this is a relevant technique for that as well. Okay, so I wanted to spend a few minutes on this because it's a different category of algorithm that might be interesting. Okay, so I want to end in 9 minutes, but let's just summarize what we've seen in terms of machine learning. So really, we've talked about several ideas. The first one, classifiers, is just a way of going from brain image data to the information content. And that's a very useful technique. Then we saw this kind of generative model that went from words through these intermediate semantic feature vectors to actually predicting brain activity. And the idea that we could extrapolate, we could train a model that extrapolates beyond the words that were in the training data because it went through this intermediate encoding of the words, the categories, in terms of this feature vector. Zero-shot learning is the same idea, except that if we reverse it, then we can go from the observed images to the categories, those thousands of possible categories. Again, extrapolating beyond class labels we've seen because we're using these intermediate features. And then we also saw some unsupervised methods. I mentioned PCA, but canonical correlation is the one that we spent the most time on. So you see a lot of the algorithms that are kind of bread and butter for machine learning, but they come into play when you get to a particular data set and a particular set of scientific questions you're trying to answer. Then you have to kind of custom design and creatively assemble a system based on your toolkit. That's what we've seen. So then let me end the last 7 minutes by showing you a sample of some more recent things we've done. And this is based on a different kind of brain imaging. So the wonderful thing about fMRI is we can see with 1 millimeter spatial resolution where the activity is. But we can't see very well when that brain activity occurred. Because fMRI is actually measuring oxygen fluctuations in your brain. And those have a time constant of 5 to 10 seconds. So if I flash a light at you, it'll generate a quick burst of neural activity which will almost immediately die out. But the fMRI signal from that impulse of neural activity will look like this. Half a second, 2 seconds, 5 seconds, it'll peak. And then it'll decay back to 0 by about 10 seconds. So temporally, it's very blurry in terms of telling us when the activity occurred. Magnetoencephalography is another instrument we've more recently been using that has not quite as good spatial resolution. It's more like a 1 to 2 centimeters spatial resolution. But the time resolution on an MEG, it's measuring literally magnetic fields coming out of your head that are generated by very tiny currents in your neurons using super cool magnets. It's very amazing technology. But this temporal resolution of MEG is 1 millisecond. Okay, so this is interesting. This is interesting because 1 millisecond is fast compared to the speed of thought. When you read the morning newspaper, do you know how fast you read? How many words per second do you think you read? I didn't know this either. Marcel told me. 3 words per second is the average reading speed. So maybe 2.5, depending on if you've had morning coffee. So with fMRI, you're going to read a lot of words, and we can't see what's going on inside while your brain is understanding even one word. That's all blurred together. But with MEG, we can. So I want to show you a movie of a person reading the word hand. And we're going to go millisecond by millisecond. Turns out it takes your brain 400 milliseconds to understand what the word is. And I'm starting the clock here at 20 milliseconds before the word appears on the screen. And you're looking at the left side of the brain. And here's what the brain activity actually looks like. Okay, 40, 50 milliseconds, 90, 120, 180, 220, 300 milliseconds, 400. Okay, your brain just understood what the word was. So there's a tremendous amount of neural activity going on in your brain, figuring out what the heck that word is. And it's obviously all over the place. So it's not a static image. There's tremendous amount of temporal dynamics going on. So with this data, we can actually start to ask questions like, what is the data flow? What is the information flow in the brain during those 400 milliseconds that it takes to understand a word? Yes?
How did you know that after 400 milliseconds it's understood?
Say that again?
How did you know that it took it 400 milliseconds to understand?
Ah.
Because I still saw something.
Excellent question. How did I know that it took you 400 milliseconds to understand the word? Two ways. There's a lot of behavioral data in the literature that shows that people express surprise of different types. If I say, I parked my car in the refrigerator, 400 milliseconds after I started saying refrigerator, your brain kind of goes, there's a signal in your brain that shows that you're very surprised. So that happens in exactly 400 milliseconds. Another reason I said it with such confidence is we found out, we trained a classifier. Now remember the spotlight classifier where we zoomed around spatially within the brain? What if we zoom around in time-space instead of in space? And in fact, that's exactly the PhD thesis of Gus Sudre, who graduated last year, now he's a postdoc at NIH. He trained roughly 1 million classifiers. He took 75 or so brain regions defined anatomically by physiologists. And for each of those 75 brain regions, he trained a classifier for each 50 millisecond window in this movie. Not just this movie, we have movies for a lot of words. And remember those semantic feature vectors that we go through? Like the 218 semantic feature vectors? So he actually trained a classifier or a regression function for each of those 218 semantic features, like does it protect you, is it alive, and so forth, for each 50 milliseconds and for each of these 75 regions of the brain. So when you add that up, that's roughly 1 million classifiers that he trained at different time, space, and predicting a different semantic feature of the word. The vast majority of those classifiers have cross-validated accuracy of 0.5. They're unable to predict anything. But some of them actually are able to predict something. And so one reason I said 400 milliseconds is that where the decoding accuracy for what the word actually is peaks at exactly 400 milliseconds if you decode it from neural activity. But let me show you what Gus then did. So he trained these 1 million classifiers, and then he built a movie not of brain activity, but of information flow. Which 50 milliseconds in which part of the brain represents the encoding of which of these 218 features? What can be decoded when and where in the brain? And it looks like this. During the first 50 milliseconds, nothing could be decoded with any significance. From 100 to 150 milliseconds, you could decode the number of letters in the word from occipital cortex, early visual processing region. So he found he can decode almost perfectly, actually like 99% accuracy. Is this a word with more than five or more characters, or 4 or less characters? Using the data from 100 to 150 milliseconds in this part of the brain. Similarly, if it was a line drawing, some of the low-level percepts, like what's the aspect ratio, or is it vertical, or so forth. But nothing semantic, just the percepts. At 150, similar. 200, but now we get the first semantic feature that can be decoded. Is it hairy? I think actually this is probably animacy, and then, so you get the idea. Over time and over space, we can see what information is actually encoded. So this is the world's first information flow, data flow diagram of what information is coded where and when in the brain during that 400 milliseconds. Nobody kind of looked at it this way before. So what it means is still a little unclear, but it answers a bunch of very interesting questions whose answers we knew nothing about before. Like, I should have asked you these questions before I showed you the result, but going in, we were wondering what goes on there. Maybe the brain sees the word, works on it, and finally figures out, oh, this is the word hand, and then it lights up that entire semantic representation simultaneously in some network. But no, that's not what we find. We find the features trickle in over time in different parts of the brain, and they move around a little bit, but mostly they stay where they were first detected. And how long did they stay? Well, I'll just show you 2 examples to show you. So this is a plot of time in milliseconds, brain region, and the color here, each box here is a classification accuracy. Or a measure of accuracy in predicting word length in this case. And the bright colors, the red colors mean high accuracy. So this shows you that at around 100, a little before 50 to 100 milliseconds after the word is on the screen, suddenly in several different parts of the brain, you can decode the number of characters in that word. And I've written the names of those parts up on the screen here. And then that information hangs around for 1 to 200 milliseconds, and then it's gone. By the 400 millisecond mark, when your brain figures out the word, there's no place in the brain where you can any longer decode the number of letters in the word, even though the word is still on the screen. Interesting. But if you take a semantic feature, like is it graspable, then you get some different brain regions that encode that well. But that persists, it starts later, but then it persists beyond the 400 millisecond mark. So anyway, this is the kind of stuff you can start to see with these techniques. And so I'm excited about the possibilities here, both in terms of brain science, but also in terms of machine learning. You can see it's one of these domains where now we have time series problems. We can start modeling the time series. We have questions of, can we come up with good algorithms that integrate this kind of high-resolution time brain imaging with the high spatial resolution fMRI data? That turns out to be a not straightforward question. And so what's the conclusion here? I think there are maybe 2 types of conclusions. One is that I think of this talk as really just a case study talk. I happen to be interested in brain imaging, so that's the case study I chose. But you can interpret this as somebody who's interested in some empirical science. I could have been interested in cell biology or astronomy or ecology or many other domains. But in all of these empirical sciences, there's a kind of decades-long trend toward higher throughput experimental data, to getting much more online and shared data, to having diverse experiments going on. And that data is kind of being put in place. And organizations like the National Institutes of Health are encouraging in their funding policies the collection of these large data sets and the sharing of them. The bottleneck, to be honest, is us. Right? There's already tons of brain image data around. We don't yet have a machine learning algorithm that can use it all and build the model that that the science is really after. Same answer, I would guess, in many other areas. I'm not as expert in ecology exactly which data sets are around and are shared, but I can tell you with high confidence that in the area of brain imaging, we already have much more data than we can jointly, simultaneously analyze. And a lot more data is being collected that's accelerating. But I think it's probably the case in most empirical sciences. So one lesson, or one thing to think about is what the future of empirical science can be and how we can kind of unleash the use of all this data by coming up with more imaginative algorithms. And then I think the second way of thinking of this talk is even if you're not interested in empirical science, you just saw a case study talk where we took several questions and saw that many of the current tools in machine learning could be used as components of a model that we wanted to build to try to get at answers to those questions. So I think those are probably the two key perspectives. So I'll end there, but I saw maybe there was some discussion. Yeah.
For a test like this, how do you know that the time information you're seeing and the order information isn't due to the fact that it's in the testing environment? It would be different outside of like the laboratory.
Yeah, good question. How do you know that, say, brain activity would be the same if you weren't lying on your back in this, absolutely still in the scanning machine, but you were eating lunch instead? We don't really know. And there are other brain imaging techniques that are more portable. The two most widely used are EEG, just scalp electrodes, which actually has the same 1 millisecond time resolution that MEG has, but the spatial resolution is very horrible, about this resolution. But you can wear EEG as you roam around, and so there's work with that. And so by kind of correlating what you see there with what you see in the scanner, it does look like they're similar. But of course, when you're roaming around, you can do a lot more diverse things. There's a second technique called, I'm blanking on the name of it, but it's kind of a portable device that measures oxygen fluctuations in your brain, which is the same biophysics as fMRI. And it's not as good as fMRI, but it's portable, so that's another thing people are looking at.
Is there a possibility to predict in an autoregressive manner?
How to regress?
Is there a possibility to predict the activities in an autoregressive
To predict the activities in what?
to predict the next moment, basically, the time given?
Predict the future, yes. Question was, can you predict the next neural activity based on the activity up till now? The answer is actually yes. It was one of the first things we tried. And well, you can predict better than random. But I don't know how excited to be about that because it turns out if you're thinking about something, you tend to think about it for a while. And so one question is, if you just predict the next brain image will be just like the current brain image, you already do better than chance. And so you have to be a little bit careful in analyzing what it means to be a good predictor of the future. We are looking at that, though, for sentence. Two of the areas that I mentioned quickly that didn't cover in this talk, we're collecting now 1,000 hours of brain image data of people reading sentences. So we're interested in much more than single word comprehension of sentences. And it does turn out that if I give you a simple sentence like, the doctor healed the patient, and I do this with MEG and I present the words every half second, then we can decode the individual words as they're on the screen. But we can also decode what the verb was after the sentence ends, using the neural activity after the sentence ends. So we say, the doctor healed the patient, and then the screen goes blank. There's neural activity at that point from which we can decode what the verb was. So, and hopefully that means it's because you're thinking about the proposition, the doctor healing the patient. So the fact that we could predict that is kind of a side effect of the fact that you're still thinking about the verb. Yes?
Have you tried any experiments on the resting state?
Resting state. We have not, but I guess you bring that up because you know some of the literature. One of the very interesting discoveries of the last 5 or 10 years is that if you put people in an fMRI scanner or a MIG scanner and you tell them to do nothing, you still see very interesting phenomena. And what you see is that different parts of the brain co-activate. There appear to be different spatial networks in the brain that go active and inactive jointly. People call that, use the term functional connectivity to talk about that. And they found that there are some just discovering these networks of brain regions that co-activate can be very useful for things like, among other things, telling how old the person is. Or some people claim there are clinical things you can tell as well, like might be relevant to detecting schizophrenia, for example. So that's another phenomenon. It's stimulus-free. People call it resting state data. You're just supposed to rest in the scanner. So if anybody ever offers you to be a paid subject in a resting state scanner, it's the cushiest job ever.
How do you feel about machine learning systems not as analysis tools, but as hypothetical neural information processing tools?
Not as analysis, but as what?
As an hypothetical neural information processing.
What do you think? So the question is, what do you think of machine learning methods, not just as analyzers of brain image data, but as a model of how the brain computes? I think that's, at some level of abstraction, a very useful idea. And in some ways, it's been around for a couple decades. People like Jay McClellan and others have talked about the brain as a parallel data processor. Artificial neural networks, for example, at some level have similar parallel structure to what we think brains do. So I think that it's a very interesting way to study the brain. I think that a lot of the work on artificial neural networks that were developed, like backpropagation, logistic unit networks, is so far, is abstracted so far from what the brain is really doing, that it can tell us only very dim it has only a very dim connection to what the brain is really doing. But I think there are people who are looking at much more realistic neural models, and I think that work has a lot of potential. So I'm glad I'm not working on that myself. I think it's a great idea. One more, yes.
There was a study where they rewired the neurons of the rat from like the eyes to the ear, and the rat was able to see. Like, are you aware of that study? And like, have you?
You mean where they stimulated the neurons of the rat and it was able to see?
Yeah. So they took the neurons connected to the eyes and they placed it in the auditory region of the brain, or like connected the eyes to the auditory region of the brain, and the rat was still able to see. So they concluded that the brain had like a one learning algorithm. There's a very general algorithm which can both lead you to both see and like hear. So do you have any thoughts around that, like based on whatever research?
I don't know the specific paper that you're talking about, but I have seen a number of papers that suggest people can learn to perceive in different ways, right? So there are things you can put on your tongue, and you can learn from tactile sense on your tongue to perceive words, for example. So I think there is a lot of flexibility in the brain in terms of routing of perceptual information. There's also a kind of another research thrust in the field is an area that sometimes goes by the name brain-computer interfaces. There's an increasing amount of work of literally putting electrical connections from the external world into the brain. Maybe the most widely used of those are cochlear implants. So people who are deaf have the opportunity, if they want to take it, to get a electrical device implanted into early auditory, into their ear that produces the stimuli, the neural stimuli, and can learn to hear that way. There's other work that isn't as developed, but is underway on retinal implants for the eye for people who are blind. And there's also, not just on the input side, sensory side, but there's also work on the output side. So for example, Andy Schwartz over at University of Pittsburgh has a lab where he has monkeys with electrical sensors implanted in motor cortex, and the monkeys control a robot arm to feed themselves bananas. There's a wonderful video, I'm sure you can find it on YouTube, of a monkey with this wire coming out of his head and a robot arm, and he's feeding himself a banana. So there's a lot of interesting work, both in terms of sensory input and control output. That has some pretty interesting clinical potential, both for blind and deaf people, but also for paraplegics and having more active kinds of prostheses. So I think in general, the interface between brain science and machine learning and artificial intelligence has been kind of needlessly, they've been distant from each other for many, many years. I think over the next decade, we'll see them come a lot more close to each other, partly because computational models of the brain are an interesting thing to study, partly because machine learning does have some techniques that work, and just maybe the brain uses similar things, and partly just because the technologies like brain imaging and these electrical interfaces to the brain, the underlying technologies are accelerating too. So all those will kind of force these fields together in, I think, a very helpful way. Okay, so let's end there. Thank you very much, and I hope you enjoy the rest of your time here. I scheduled myself a little more. I don't know if there's a lecture. Yeah, I'm going to schedule a lecture.
Yeah, sorry, I know. I'm very busy, but you can talk about that.
So, like, say I'm reading the same sentence, like say contrast drinking water. So the sequence of activation across different frameworks is the same across different contexts. And second question is, say I'm reading a sentence, contrast drinking water, and actually seeing you visualize both of you drinking water. Is the sequence of activation across different frameworks the same? I'm not trying to find the best out of
People have, I bet the answer to that is because everyone's slow enough, they kind of don't see and find and so it could be that I told you, it might be kind of similar, but still, if you think of the fine and the structure of this, it's quite different. Because, first I just said, at that point, you know that I'm drinking is something you don't go to. But in the video, it's all obvious. So the information as you feel it, so I think because of there is some interesting work. It's about change.
Oh, check out.
Very good. Yes, right. So it's not quite the same as your question.
I'll check it out. So, thank you very much.
What are you looking for?
We still have enough time to try to control the
Well, we have this book, the first person, it's like, and then if you book the second person, then you get, discount. Yeah. So we're just saving skills. Yeah, so. When I broke or something, like all the minutes. So, how do we get there?
Living today so for which one did you learn to implement the VDM?
So in India, I started talking I'm sorry that I
yeah, so I've already talked to Paul. Yeah, we have to talk first. Theory and there's the application and where you want to learn at what time. Right. So where you have to go in, or you can catch yeah. Maybe. I'm sure. Oh my God, it makes pain. This is supposed to be like what classical design. This Anam one so it's like translucent. I think there's like very few of them. Few of them just like I think that it is something yeah, they can be but not the detail. Very coarse to do. Yeah. Yeah, have you managed to talk to a lot of people? Yeah, not bad. Oh, okay. How is that going? Not bad. Yeah. Okay. It's time till Friday, right? Yeah. So that's good. Did you submit something already? Or?
Yes, submission last night.
So this is a clustering?
It's clustering. It's kind of like topic model because you have to find the it does, yeah. It's kind of you have to like
yeah, but it's in
yeah.
Yeah,
no, you can do that.
Why not do that? You should try that one too. That's true.
Yeah.
Just, anyway, yeah. I mean, after the temple method is already available. The initial pre-processing you can try different ways to do the yeah. You could even just cluster on X. Or center it white and yeah. Just talk to them. Yeah. Try them, might not try them. I think it's a RAM. Except that one stop like one day, you know.
For you, going back from the average. Take off the
That's more standard.
Yeah,
We have to look for individual
It's crazy.
I can check it out. I have to ask.
They didn't tell us. Yeah, you know. You could have still here.
It's not. Is this the, am I strapped to the correct one? Is this the one? But, no, but what is this? I was hoping to get back in
Well, we are not on camera.
Please stop the line.
No, wait, it's being live streamed. Yeah, okay, it's not the Super Bowl, but I think it was. Do you have AA batteries in the back? Can you check?
Oh, there is no.
Oh no, they are AAA.
Oh, those are not.
They're all good.
Oh, they're all done.
No, we actually had a charger. We swapped them this morning, so. No, but there was a charger. No, basically that chart is somewhere.
Let me check it out. How many does it?
It needs to, actually, okay, got it. Yeah, they are charts here.
It's fine.
No, but they.
It's missing, like, because
Well, that was.
it was here and then it was missing. You got taken off. So this one.
No, actually leave that on. Leave it here. It's going to make myself secure.
No. It's broken.
Broken.
What happened?
Top broke of the microphone clip.
It's not that complicated.
Yes, I'm going to abuse you. No, he just. Yeah, he basically separated it. Well, I know, but it doesn't. So that's why.
But even like,
Okay. Basically, I think I'll let Andy do that myself. Basically, okay. Okay, basically, make it not fall off.
Yeah, but also.
Yeah. Okay.
that's perfect.
As long as it doesn't irritate you or something.
Is that okay?
Yeah, that's okay. So, last lecture this morning is for Anima, and that takes us 2 minutes.
Okay, so this is the last lecture on tensor methods. So I hope in the last 2 days you got a good idea of what tensor methods are about, how we can go about applying it to a variety of different latent variable models, and how we can analyze these methods, right? So, I mean, kind of the idea is, although these are non-convex problems, they have a lot more structure than general non-convex problems. So we are able to provide guarantees. In particular, the main property is that when it can reduce it to a tensor form which has no spurious local optima. So you know that any like say gradient ascent kind of method would converge to a correct solution, and that's why with these tensor methods we're able to provide guarantees that we can consistently recover the parameters. And we saw that we can handle a wide range of latent variable models. Kind of the main intuition is like, the statistical constraints, especially conditional independence constraints, gives rise to additional information about the distribution. And this is reflected in tractable forms in the moment, right? So if you write out the tensors, you can reduce it to tractable forms, and that was the main kind of overall view of thinking about a range of different latent variable models in a unified viewpoint. So today I'll be talking about more practical issues like, okay, so I have this method that can compute these parameters. How does it work in practice? And in particular, how does it compare to other methods, right? And how do I scale it up to large data sets? So I'll talk about some of our experiences. First on a single workstation. We've also implemented on GPUs, and these methods are in fact perfectly suited for GPU operations. And most recently, we've been looking at a cloud-based implementation on Reef, and you've seen lectures by Marcus, and that's going to continue this week on how to do implementations on Reef. And these tensor methods are also very well suited to be implemented on this platform. And this is still ongoing work, but I'll give some insights on what we've found so far. So just to recap the basic tensor factorization method, what we had was looking at, let me start with the toy example we had in the first lecture. So this was the topic model with just 2 topics, and there was only the single topic in each document. And I just showed in this toy example that there were just 3 words in the vocabulary, right? So this was the multi-view model that each document had 3 words, and they were just like D was also equal to 3, so I had 3 words in my vocabulary. And the multi-view assumption was that all these words are conditionally independent given the topic. And my estimation goal was to find these topic probability vectors, which is the probability of different words under different topics, right? So this was a D by K matrix, and I wanted to estimate this matrix. And this was just, just the sample code I showed to generate the samples. And once I had the samples, we computed the second order moment, which is the co-occurrence of 2 words in my documents, in the set of documents. I'm asking on average, what is the probability of co-occurrence of any 2 words in the vocabulary, right? So I'm going to compute this empirical moment, and then we did rank K SVD on the second order moment to obtain the whitening matrix. So the intuition of whitening was to implicitly change the system, right? So originally I had these vectors here, A1 and A2, in D-dimensional space, and they're not orthogonal in general. But I'm going to convert it into an orthonormal system in K dimensions. So this whitening step reduces the dimensionality from D-dimensional space to a K-dimensional space. And as we are doing it, we are also making it an orthogonal system. And so that was the idea that the first operation is SVD. So I'm going to do a rank K SVD, and K is usually small in our applications.
But we'll see how to, again, scale it up to like large amounts of data, like when D is large here. So keep in mind, this is the first step. It is to do SVD. And once I have the SVD, I'm going to compute these whitened samples. Right? So I'm going to reduce my samples from D-dimensional space to the K-dimensional space. And once I have this, the idea is to now operate on the tensor with whitened moments. Right? So this is now the third order tensor, which is the co-occurrence of 3 words in the vocabulary, but then I'm whitening the tensor. So now I'm computing this empirical moment using the whitened samples. And the power method we saw in the last 2 lectures, you can think of it as gradient ascent on for the problem of maximizing the Rayleigh quotient. Right? And this is just a simple multilinear operation. So you take these samples, and I'm computing this inner products with my current estimate of the eigenvectors, and I'm normalizing it, and I'm kind of continuing this operation. And this was the idea that the power method recovers these eigenvectors. Right? And so this was the power method, right? So I'm doing this quadratic operation, I'm normalizing it, and once I converge, I'm going to subtract out those estimated eigenvectors, which is the process of deflation, and I repeat again. And we saw that in practice that this, for the simple example, that there is fast convergence to the eigenvectors. Right, so this was just the toy example, but now if I want to implement this on a large-scale data set, on a real data set, what are the optimizations I need to think about further? How do I ensure that it becomes scalable to a large-scale data set? So that's what we will see today. Right, so in particular, we've looked at 2 applications, and mostly I'll be focusing on the first one here in the talk, which is the task of community detection. So yesterday I showed you how we can employ the tensor methods for learning communities, hidden communities in networks. So we saw this, there is the classical stochastic block model, which posits that, there are nodes which belong to different communities, and the probability of an edge is only dependent on the underlying communities, right? All the edges are conditionally independent given the community memberships. And then there is the extension we saw to mixed memberships, where nodes can now belong to multiple communities. These are the so-called mixed membership stochastic block models, and we saw that the tensor methods can also be extended to the framework where now nodes can belong to multiple communities. Right? And so today we want to look at examples where the size of the network can be like up to some millions. So I'll show the instance where on a single workstation we can handle graphs with millions of nodes. And our goal is on the cloud, we can even push it further. We can, make it as large as just requiring more cores, so we can parallelize it to a large extent. And the communities, usually we think of them as a few thousand, right? So typically we want to mine for a small set of communities from this graph data. And similarly, you could think of like the topic model setting where the size of the vocabulary is usually few 100,000, maybe up to 1 million. And you have a large number of documents, usually millions of documents, right? So this you can think of them as samples, like how many samples you have. And again, the number of topics you'd like to mine is usually a few thousand. So the question is, how do I handle this scale, right? So the main challenge is this. Here in the graph setting, it's the size of the network, which is large. And in the topic model setting, the number of documents and the size of the vocabulary are large. So how do I make it scalable to this setting? And that's what we'll see today. Okay, so the main papers on which the talk is based on, so this paper, is like my students, Farong Huang, Niranjan should be in the audience somewhere here, and Mohammed. So this we, did it last year, and an ongoing work on implementation of REEF. We still don't have the write-up out. We are still running the experiments. So in that, my student Farong interned at the Redmond lab, the Microsoft Redmond lab, Sergey is also involved in the project. There's Paul and Nikos who are also involved in this project. And the CPU and GPU codes are available on GitHub. I mean, I guess the title got cut out here, so you can check my website for the full code. So the codes are available, and we soon plan to release the REAP code as well. So that'll be available online as well. Okay, so let's now just recall the tensor method for community detection, and then see how in each step we can incorporate techniques to make it parallelizable and scalable. So, I mean, as just to recall from yesterday, what we had was this notion that these communities are groups of nodes, and then there is kind of a common connectivity pattern between nodes in the same community. Right? So the simplest case is this stochastic block model, where nodes just belong to a single community, and here there is more connectivity within a community rather than outside. And we saw that with mixed membership, now you have nodes belonging to multiple communities, and you have this very connectivity based on how they belong to different communities. And kind of the common unifying notion is that all these edges are generated conditionally independently given the community memberships. And we are assuming memberships are drawn from a Dirichlet distribution. Right? And so depending on the concentration parameter of the Dirichlet distribution, we have varying amounts of overlap in the community. So this is the generative model, but my task is that given the graph, I'd like to recover the community memberships. Right? And if you recall, the idea was to now mine for particular subgraphs in the counts of these subgraphs by partitioning the nodes and looking at like these star with 3 leaves, right? How they occur across the partition. So the very first step was to just divide the nodes into 4 sets. And I said that in theory it's fine to have random partition, but in practice you'd also maybe want to optimize for like having a large number of edges across the cut. Because there are more, if there are more edges, there's more information about the communities they belong to. And the idea is for every triplet here, I'm counting how many common neighbors are in this outside set X. Right? So that was exactly this count here that I'm looking at for every triplet ABC, how many common neighbors are present in X. Right? So G is the adjacency matrix. So I want to have edges, all these 3 edges present, and then I kind of count it as an X, and how many such nodes are present. So I'm summing over X here. And this was a tensor form of the same object. So this is a 3rd order tensor of size equal to the size of set A times the size of set B times the size of set C. So this is a tensor of order n cubed, right? So because n is the number of nodes in the network. And this was the main idea that once I have this partition nodes and I looked at the set of edges to each of the subset A, B, and C, this formed a multi-view model. So conditioned on the community membership with node X, all these set of edges, right, into these 3 subsets are conditionally independent. And also each one is a linear model. So that's why we could reduce it to this multi-view linear model that I described yesterday. And to recall, the main 2 moments we had to compute, right, was the 2nd order moment, which required like essentially counting for 2 stars, that is between say A and B. I'm asking how many 2 stars are present between them. That's essentially this pairs matrix, right? And then I'm symmetrizing it, so I'm kind of doing some pseudo-inverse operations and some multiplication operations. And then I'm forming the 2nd order moment. And I'm also doing a 3rd order moment where I'm looking at the symmetrized versions of my neighborhood vectors, and I'm taking the outer product of them to get a 3rd order tensor. Right? So we're going to be operating on these 2 statistics. And the theoretical reason is that in expectation, these are multilinear forms of these unknown vectors U, right? So the second order moment is a bilinear form in the UIs, and the third order moment is a trilinear form in the UIs. So this is the theoretical justification of why we consider these moments. But now let's just review the operations we are going to do on these statistics. So we have a pairwise statistic, which is a n by n matrix, right? So order n by n. And a third order one is like an order n cube object. So we're going to be operating on this. And just to recall the tensor method, what we're going to do is compute an SVD, in fact a rank k SVD of the second order moment, where k is the number of communities. So for now, I'm going to fix k, but in practice, you can also, do cross validation. You can try different values of k and see which one has the best perplexity or some score that you're, interested in. So yeah, there's also a way to estimate k, but for now, let's fix k. So I'm going to do an SVD rank k, SVD of the second order moment. I'm going to whiten the third order moment to obtain this tensor, which is k cube, right? So I've reduced my tensor from n cube object to a k cube object. And then I'm going to do the power method, right? So what we saw was to do the power method on this whitened tensor, but we'll see in practice there are different versions I can do, right? I could do like stochastic gradient descent. There is like alternating least squares method. So the various ways to do the decomposition, the orthogonal decomposition of my tensor T. And then finally, we need to do the post-processing because I've only decomposed a k cube tensor, so I need to recover the communities from this information that I have, from the eigenvectors and eigenvalues that I've recovered. I need to get back the communities. And finally, we need to see how to compute the error scores. This could be the perplexity, or which is the version of likelihood for the model, or if ground truth is available, we can also validate against it. We'll see that in many of the examples, there is ground truth available, so we can have alternative evaluation criteria based on that. So this is just a rough overview of the techniques, right? So let's first focus on the first step, which is whitening. So this requires the SVD operation. So what we need is, so first I need to do some symmetrization, right? So I needed to compute first this pairs matrix, which is an n by n object, and then I need to compute some pseudo inverse, and then do these multiplications. So even in just this step, if you do it naively, it's possible to go wrong, right? Because what I have is an n by n object, and n is like millions or even more. Then even storing this and doing the product, right, is not scalable, right? So right now we are just thinking of running it on a single workstation. So we want to optimize for both space and time as much as possible. So so this was the operation, right? So if I had to do like manipulations on like n by n objects, right? Take the pseudo inverse, even just storage. Like for instance, if I had like a million nodes, and in general, we'll see that graphs are sparse. So the pairs matrix by itself is a sparse matrix. But on the other hand, if I computed the pseudo inverse and tried to store it, that's a dense object. Right, so and if I just simple calculation of the memory, it says that I would need like about 58 TB to store these objects if n is a million. Right, so if I did this naively, this is not at all possible to do it in a single workstation. Just a simple operation, right? So this is just the very first step of the tensor method. But then, we know that the pseudo inverse has structure, right? It's rank k. I mean, we are only going to do like kind of rank k representation of these pairs matrices and then manipulate them to get the pseudo inverse. So my pseudo inverse really is like of this form where it has a rank k representation. So instead of like kind of, so my storage is now, right, it's much more promising because I have to just store nk objects, right? So the space complexity is just n times k. And typically just this pairs matrix, it's just n times s, where s is the sparsity level, right? So think of like the sparsity of every row. So usually these graphs are extremely sparse, so I'll never run into an n square object here. Right, so I can store just the pairs matrix by themselves as like, because they're sparse, I can still store it in a single workstation. But the problem was to store inverses of these matrices which are not sparse. But then I know that I only care about the rank k approximations, so I'm going to store it as a rank k approximation. And so that is still manageable in a single workstation. It's about like a few GB instead of like TBs. Right, so there is just the very simple, trick makes a big difference in these operations. And that was one aspect, but it's still like for computation, right? So in order to do this product, I can also like kind of essentially just order the product in a different way. So like the intermediate quantities that I'm storing is also now just n by k objects. Right? Never n by n dense objects, because now this is still like an n by k, this is an n by k. Right, so just, I want to, this is quite, I think, simple to see in retrospect, that when I have to do these multiplications, I have to manipulate them as like, these pseudo-inverses in terms of like their rank k approximations. And I have to do the multiplication in kind of the right order to ensure that I store only n by k objects. So, and yeah, so that's why we can, handle with a small amount of space, even like, matrices up to 1,000,000 by 1,000,000, which are sparse, we can handle them in a single workstation. Okay. So I've now computed the symmetrizations that are needed. Now I want to do the SVD. Right. So again, if I did the usual like rank k SVD of an n by n matrix, the computational complexity is n squared k, right? Which is again not scalable if n is millions. But there are there's a whole range of randomized low rank approximation techniques. Particular, I'm just mentioning a few here. Indeed, this is a very exciting area of research on how to come up with fast randomized methods and how we can make it, how we can get it. So you won't be getting the exact SVD, but there are even theoretical guarantees of getting good approximations when the k is reasonably small. So, for instance, what we can do is I've just shown one method here, and I've just shown like two possibilities. If the pairs matrix is dense, you would just sample a random matrix, for instance, with Gaussian entries. But if we know that in the applications we are interested in, we have this matrix to be a sparse matrix. And in that case, what we're going to do is do like column subset selection. This is the paper by Clarkson and Woodrow. And so I'm going to just like randomly select columns and put random signs on them. I guess this is ±1, so this is so with a random sign here. And so once I get this only subset of columns, so think of like the number of columns I choose. This k tilde is like a few times k, right? So k is usually thousands. So if k is 1,000, I'm going to choose it like say 2,000 columns or 3,000 columns. So I'm going to choose a few more, like some factor of the rank that I want to estimate. And so this is my matrix M2 times S, right? So these are randomly selected subset of columns with random signs. And I'm going to find an orthogonalization of it. So this is the Gram-Schmidt orthogonalization, for instance. And then I'm going to compute this matrix Z, which is just a k by k matrix. So I'm going to reduce my n by n matrix to just a k by k matrix. And I only need to do SVD on this k by k matrix. right? So I don't need to do the full SVD. I'm only doing SVD of a K by K matrix. And then there are just some simple manipulations to, compute the SVD of like M2, right? So this V is like the set of singular vectors, V M2 for the original matrix M2, and L is the set of singular values for the original matrix. So it's a very simple set of steps. I'm doing some either multiplication or like selection to get a tall thin matrix, and then I'm doing reducing it to a K by. I'm doing orthogonalization, and then I'm reducing it to a K by K matrix, doing the SVD of this K by K matrix, and then again projecting it back to this n-dimensional space. Right? So now it turns out that the computational complexity of this randomized method is much better than the computation for exact SVD. So if the sparsity level of each row is S, and I have like C cores, it is NSK by C plus K cube. Right? So this K cube is coming from doing the SVD of this K by K matrix. Right? So it's K squared times K, which is K cube. So when usually K is small enough, this is this is a fixed cost that you have to pay. But then you can parallelize all the other operations, right? As long as you have enough cores, the other operations become almost irrelevant. So as you have larger number of nodes, you just need larger number of cores to handle the operations. And so almost like this first step is the bottleneck, and indeed that we have access to a large set of techniques to do fast computations for SVD, right? So when I want a low rank approximation of a large matrix, I can have a whole range of techniques, and I've just shown one possible technique to handle this. So that's how in the first step we can get this computational complexity, which is essentially K cube, right, if I have enough cores. So it's independent of the number of nodes if I have enough cores. So this was the whitening step. So once I've whitened it, I want to now do the tensor decomposition on the whitened samples. Right, so I had this M3 object, which is, this D should be N here. So I have an N cube object, but instead I'm reducing it to a K cube tensor because I've done the whitening. And I want to do a decomposition of this K cube object. So the method that we saw before, for conceptual reasons, this was easy to study, as well as like the analysis of the error buildup was easier to go about, is this power method with serial deflation, right? So I'm recovering the vectors one by one, and I'm serially deflating them. But then in practice, it's much faster to do them in parallel, right? So if I have to wait for each vector and then subtract it out, then do the other, it can be slow. So an alternative technique that is employed quite extensively is this alternating least squares update. So here what I'm doing is I'm fixing I'm going to introduce these matrices A, B, and C, right? And I'm just trying to minimize this objective function, right? So I want to find this decomposition with components A, B, and C, right? Which fits my tensor T. And then in each, it's called alternating least squares because I'm going to fix two of the modes. For instance, I'm going to fix B and C. I'm going to update A. Right? And we know it's linear in each of these variables. So if I fix B and C to update A, it's a simple linear operation. It's least squares. So I can do this efficiently. And so I can cycle between fixing two of the modes and updating the third one and go about it. And this is what we implemented on the cloud, so I'll come to this method a little later. But still, when the number of nodes is large, if I did this as a batch, this is expensive, right? So there are two possibilities. If I had to, if I didn't compute this tensor, for each pass, if I had to compute the sum over all the nodes, right, then this is expensive. The other option is to form this tensor and store it. And if I have enough memory, I can do it if k is not too large. Otherwise, this also becomes expensive. So this is if I did this as batch, but I could also do it as a stochastic update. So here I'm never forming this tensor explicitly, and with each new sample, I'm just updating my gradient, and then just touching just one sample at a time. So here this GA is like a whitened sample of my neighborhood vector to this subset A. And similarly, I have these whitened samples here. So, and I'd like to think of, optimizing this objective of finding a set of vectors that fits my empirical tensor. Right? And I've used this parameter theta to think of like a trade-off between an orthogonality cost and a correlation reward. Because the intuition is I'd like to have these set of VIs to be orthogonal. So so with this I would only get like rough orthogonality, but in practice that suffices, right? So I don't need to maintain a strict orthogonality, and this is much cheaper to do. So I'm going to put as I increase theta, there is a much more advantage in having orthogonal vectors, and at the same time I want to have vectors that are well correlated with my set of like the empirical tensor. So I'm balancing between the two. And so on this objective, I can do a stochastic gradient descent. And to do this, this is exactly the gradient. So this is my update in each step. Beta t is the step size. And you'll see that the operations are essentially just products. Right? So in each step, I'm getting a new sample here. This is GA, GB, GC. And these are the whitened samples. I'm computing inner products with the current estimate of my vectors, right? Set of vectors VIs, and then I'm just updating them. Okay, so think of this as like a set of have these whitened vectors here, and like computing inner products along this set of fixed directions, right? These VIs, right? And then I'm also computing like a set of inner products among the VIs themselves, right? And the idea is that if the VIs are mostly orthogonal, this term is small, and if the VIs are well correlated with the samples, this term will be large, right? So that is the balance between maintaining orthogonality and also having good correlation with my empirical tensor. So I can do this trade-off, and so you see that in practice, I don't have to form the tensor explicitly. So I'm just taking a new sample, I'm computing the gradient, which is essentially this multilinear form here, right? And then I'm doing the update. So all that's the decomposition of a tensor. The advantage is you never have to form the tensor. You don't have to form and store the tensor, so it becomes scalable. Okay, and that's why in like the space complexity, you only need to like maintain like kind of k-square objects, right? Because there's I have like in dimension k, I have k eigenvectors, and that's all I need to maintain, right? So I'm only storing those. And the time complexity is like if I had c cores, it's k cubed by c for each iteration, because I'm doing these k square inner products, right? Because I have to compute k square object, k square entries, and each inner product is like order k because I'm doing an inner product in k dimensions. So you see that this is again when k is small, this is in fact very negligible, and in fact I don't even need too many cores for this step. So the first step is mostly the bottleneck, which is to compute this SVD of an n by n object, right? So, and that we can do with randomized techniques. But after that, the tensor decomposition with stochastic gradient is extremely fast. And the very last step, once I've found the eigenvectors and eigenvalues for my whitened tensor, I have to get back the community membership. So I won't go into all the details. There's some normalization parameter that's required here. You can refer to that in the paper. But the idea is if I have this set of eigenvalues and eigenvectors from my, from the stochastic gradient operation, and G is my adjacency matrix, I essentially have to do some simple, matrix products to get back the communities. And typically in practice, we'd like to threshold the values because I want sparse memberships, right? I'd like the nodes to belong to a few communities. So I'm going to do some thresholding after I do these operations. So again, these operations are fully parallelizable because these are just products, right? Matrix products. And again, if it's sparse matrices, you have even better efficiency. So if S is the sparsity level for row, you have like NSK by C. So if you have sufficient number of cores, again, you can make it fully parallel. And in the end, we are storing just like these community vectors for n nodes, and each one is k dimensions, so it's n times k. Right, so this operation again can be made extremely fast. Yeah, so that's kind of the overall, space and time complexity for the tensor method by first using the randomized SVD techniques, maintaining rank k approximations for computing the symmetrizations, then doing stochastic gradient on my Viton tensor, and then doing like a final post-processing where I get back to the n-dimensional space, but that's some simple matrix product operations. So you see that the overall time complexity, if I had enough number of cores, is essentially just an SVD of a k by k matrix. So this is k. And the other steps are very, they're in fact very fast in practice. And here I've also in the column just shown the comparison to the stochastic variational approach. So Dave Bly's group and Eric Zing here. I mean, a lot of researchers have been looking at variational techniques on the mixed membership stochastic block model, and there, the main kind of quantity for complexity is the number of sample node pairs. So this could be as large as the as n squared, because n squared is all the node pairs. But in practice, they find that you can do it by sampling just a subset of node pairs. So think of m as between like n and n squared. And so in each iteration, I have this complexity, which could be as large as n squared times k, right, in the worst case. And again, parallelizing this, again, there's a lot of exciting research going on, including here at CMU, but it's still, like not as straightforward as parallelizing matrix and multilinear operations, right? So with matrices and tensors, I argue that is a very big advantage that parallelization is trivial, right? Almost all the operations are just embarrassingly parallel. So, and that's the I would argue is a big strength of these methods. Yeah. So now let's so I'll talk about some additional optimizations we did on the code, and also how we went about looking at different data sets and what are the validation mechanisms. So we did both GPU and CPU implementation. So in fact, this method is ideal for GPU implementation because the GPU has a lot of cores which are very simple cores, right? So they can handle only simple operations, but we also need only simple operations. We only need either matrix products or some kind of inner product addition, like simple BLAS operations. Right, so they are ideally suited for GPU implementation, but the downside is that the memory, right? So the GPU memory currently is extremely limited. I mean, I think it's mostly like the the reason behind it is that the technology hasn't yet caught up. Like there are a lot of these machine learning applications which can now benefit from a lot more memory, and I think that will happen in the coming years that we would have GPUs with a lot more memory. But currently, this is in fact the major difficulty in implementing these methods on GPUs, because once I don't have enough memory on the GPU, I'd have to kind of do a lot of out-of-core operations. And in that regard, the libraries are still not, sufficiently developed. So I think there's a lot of room for, incorporating like linear and multilinear operations on GPUs. But I feel that there is also a lot of work to be done in terms of developing still, good libraries. In fact, when it comes to sparse implementations, I think there is again a lot of room for improvement with GPU libraries. And in fact, it's kind of a non-trivial problem because with GPUs, like how do you have a sparse representation and how do you communicate it to the GPU? I think there's still a lot of ongoing research. So what we did was we did a GPU implementation, but we only did it as a dense implementation, meaning that all our manipulations are assuming that the matrices are dense. So if they're, on the other hand, these graph, the adjacency matrices are sparse, right? So we are not getting the benefit because of sparsity. So we also did a CPU implementation, but on CPU we have good libraries that do all the manipulations in sparse format. So we use the Eigen library, and there are sparse, like you can do all the implementation in sparse representation, and that is also very important to get the to get us to work on a single workstation up to million nodes. So we could just store them as sparse matrices, do the manipulations in the sparse format. And so with respect to the GPU, like I said, memory was a bottleneck, so we had to carefully partition our data and kind of send them in blocks when the when the graph becomes large. So that was one of the challenges. The other challenge is for even iterative updates, right? So think of the stochastic gradient update. So what I'm doing here is I'm looking at Whiten vectors, and then I'm computing these inner products, and I'm updating my estimate of the eigenvectors. So, but the challenge is each time if I, the simplest way to code for a GPU, if any of you have done GPU coding, is the so-called standard interface. So here, what essentially the communication is handled in a standard way. So each time, all the variables that need to be computed are kind of communicated from CPU to GPU. The computation happens in the GPU, and then you transfer back everything. Right? So because I want to compute these eigenvectors, I have to transfer them in each iteration to the GPU and then back. So this can be quite expensive, and because I want to, and these eigenvectors are not too large, right? Because they're k-dimensional vectors. Their k vectors each is k-dimensional. So that's why we can now do instead a device interface mode for this iterative operation, where I store the eigenvectors in the GPU itself. So I don't have to communicate the eigenvectors back and forth. And each time I'm just like, taking a new Whiten sample from my CPU and updating these eigenvectors. And this in fact gives a big boost, quite a big boost compared to doing the standard interface. So this magenta line here is the so-called standard interface, and CUDA is the library we've used. So this is the linear algebra library for GPUs. This is built on CUDA. So if I did the standard interface, I get this scaling, right? So the x-axis is the number of communities, right? So the k, like so I have like k eigenvectors, each of dimension k, and this is the running time. So you see that this is the magenta line with standard interface, whereas if I did the device interface, I get like almost like a 10-fold improvement in my running time. And the other, so this of course there's the standard MATLAB interface on the CPU. This is like the coldest, but like the toolbox for tensor, and that of course there's no competition, right? In fact, yes, the intention is not to kind of directly compare, but just I showed here as a way to see that it's pretty bad. And the other one is like the CPU implementation, which is like the Eigen library. And that's, again, like the GPU with the device interface is the best, which is intuitive because you have very efficient operations on the GPU compared to the CPU operation. So especially as I increase K, it would be much better to do it on the GPU. So, although we haven't done it, you can think of even hybrid implementations, right? You could, for instance, do like randomized SVD on the CPU, maybe even on the cloud, and then you could do this, stochastic gradient descent for tensor factorization on a GPU. So if K is small enough, meaning K is a few thousand, you can still fit all these eigenvectors in a GPU. So and this then operation can be very fast. So there's a lot of interesting, engineering questions on how to kind of use the resources, say on the cloud, on local machines, on the GPUs to have fast computations. Okay. So these were some, I think nice, questions here also of how to minimizing the communication. So if I have both GPU and CPU, how do I minimize the communication? And we see that although the device interface was harder to code up, there are gains by doing that. So that was in terms of like the GPU implementation, and now we want to see that once we have carried out these operations, how do we go about validating it? So in the experiments that I'll show you, we have the ground truth information. So we'll see, for instance, we have information about, like, say, in a DBLP data, where the nodes are the set of authors, right? And the edges are when two people co-authored a paper. We also have this ground truth of where the paper was published, right? And you can think of them as communities. So the set of journals and conferences as communities, right? And then the question is, can we recover, so our estimated communities, are they close to these ground truth communities? So I have now an assignment problem of how to relate the estimated communities to my ground truth community. So now we come up with a very intuitive error measure to compare these estimated and ground truth. So pi is the ground truth communities, pi hat is the estimated. And so we'll do kind of a soft test. So we'll think of a notion of p-values, right? And based on that, we will do a pairing of how how likely is it that this estimated community is related to this ground truth community, right? So I'll compute p-values, and then based on like the significant ones, I'm going to declare them as paired. So for instance, if these are like set of ground truth communities, these are set of estimated communities, that they need not be even the same number of them. Based on p-values and thresholding, I infer a set of communities. Right? So it may well happen that a community here may not even have a neighbor here, right? Because my p-values tell me that there isn't a statistically significant relationship between them. So I'm gonna, and this is something I think is like some more, better motivated to do in terms of how to relate my ground truth to the estimated community. Right? So once I have this pairing, I can then compute the error measure based on like how do the entries differ in this paired set of ground truth and estimated communities. So here this set of edges here are the set of inferred edges based on p-values, and I'm going to ask like an L1 error for every estimated community and the ground truth. And the notion is that if I have a lot of false pairings, then I have a large error, right? So I'd like to have a good assignment of my estimated to ground truth community, and the weights are also small. I mean, the difference of the weights is also small. In that case, I have a small error score. And so that's the idea that first. When I have these estimated communities, I'm going to relate them to ground truth communities using p-values, and after I do the pairing, I compute an L1 score and normalize it suitably. So that is the evaluation metric. So now let's see how we how do we, do in practice, right? What are the so we did it on a small network of Facebook with just 20,000 nodes, but we here had the ground truth information. So this was an anonymized data set where, it was in a university, like what are the majors, what are the dorms, what are the high schools that people went to. So we had this ground truth information, and so this was interesting for us to check out, although this was a small data set. And the biggest one we did was this DBLP, which is up to 1 million nodes. And we also subsampled them with 100,000. We also have results for that. So in DBLP, the communities are like the journals and conferences that people publish. So we also looked at a kind of more recommender system setting, where on one side we have a set of users, the other side we have a set of businesses. So these were reviews on Yelp, and we are even ignoring the text of the reviews, right? We are only looking at whether there is an edge between whether a user reviewed a particular business. And we looked at the stars, so we did use it as a weighted graph. And so the first thing is the running time. So what we did was to run the variational code from Dave Bly's paper and compared it to our method. And you see that even on like a small network, there is in fact no competition, right? So this was just both on the same workstation using a CPU code. So there is a huge difference in the running time. That's because the variational method is very expensive. Like in each iteration, we have these expensive operations, as well as we need a lot of iterations, a lot more than typically that's needed for these tensor methods. So you see that there is a big boost in the running time, and in fact we can go all the way up to 1 million nodes on a single workstation. So it was just about like 1.5 hours to be computing about 100 communities on this DBLP data. So yeah, so we can, so we have a good, in fact, a very big boost in running time compared to the variational techniques, and we also have very good error scores as well. That's the error score that I described in the previous slides. So since I'm almost out of time, I want to just, so in summary, we have now almost the best of both the worlds. We have good recovery accuracy, as well as very fast running times. So these, in fact, these are just simple linear algebra and like multilinear algebraic operations. So that's why we can have them be run very fast. Since I'm out of time, I won't talk a lot on this on the cloud-based implementation. This is something we are just starting to do. So all I just want to say is just our preliminary experiments on the New York Times dataset. We've seen promising performance compared to the stochastic variational technique, and compared to a simple like map reduce operation where it's very expensive to do iterative updates, right? So that's why you see that overall this is hugely expensive. Like if I had to do these iterative operations to get the tensor decomposition, like on a map reduce framework, it takes like 4 hours, which is ridiculous. But on the other hand, as I just have do a reef-based implementation, and as I have more nodes, I'm like able to get that to be very fast. And we want to now scale it up even to a larger cluster, and we hope to have it to be much better than the times that I've shown here. Okay. So concluding this talk series, what we saw was these tensor techniques have good theoretical guarantees, but you see that even in practice, these are easily parallelizable. They're scalable to large data sets, and also have good accuracy, both in terms of like good perplexity scores. I didn't show them, but they're available on the paper, and also like ground truth validation as well when we have ground truth. And so that's how I see these techniques as having a lot of interesting challenges in terms of like theory, right? So how we can push them beyond in terms of especially learning overcomplete models and getting good theoretical analysis. And as well as in practice, you saw today, there are interesting questions of how to do like a cloud-based implementation, a hybrid CPU and GPU implementation, how to come up with fast randomized techniques for processing on matrices and tensors. So I find it a rich set of questions here to look further into. Thank you. Questions? Yeah.
So in the real implementation that I can implement of Lightning and parameter,
Yeah.
responding on the numericals, the evening issues.
So, I mean, again, yes, so that can be an issue if, I mean, you have to kind of also, I mean, these are mostly, when you're doing the inverses, right? It could be an issue if K is too large, like, if the matrix is really not rank K, or like the eigenvalues are really bad, that's when the issue comes. So you could do some regularization as well. So that's, yeah, so mostly that's the main place where the issue comes.
Did you try use the GPU arrays in MATLAB, or did you directly port it to CUDA libraries?
So we did it directly on CUDA. We found like with the MATLAB, it was I think much slower to through MATLAB. So this was much more efficient to do directly. I mean, there's a lot more work in terms of programming, and especially this device level interface, right? I can't get it through MATLAB.
The follow-up question is, do you use just one GPU card, or do you use multiple GPU cards?
Just one for now. And again, this is mostly due to lack of good library support already existing. I think they're coming up, I mean, day by day, there are a lot of new libraries. But yeah, but if you know of any good libraries with multi-GPU support, it would be very interesting. Yeah.
Did you try to run it on Xeon Phi?
On
Xeon Phi?
Xeon
Phi from Intel, the acceleration?
Oh, no, we didn't try on that. No. We tried on the Tesla.
Mm-hmm.
Have you tried these methods on something like restricted Boltzmann machine and other kinds of those Latin variable models?
Yeah, so I mean the challenge is these are like require this linear assumption, right? Whereas those are log linear. I mean, you can first maybe one way to do is to initialize with these methods and then maybe do variational inference. So that would be interesting to see how that works. Yeah. All right, thank you. Yeah, we can talk. So then first we do p-value adjusting. So before we do p-value and based on p-value, so you get these just say all p-values no, just like you showed it. I mean, that's what you would pay a lot more price if you had a lot more. You're just adding more, right? So it was, I mean, you can do this was related to and the weights were also different. They wanted actually, even the variational one, so in the latest nowadays implementation, the extent is better than the variational. So I think but we have to do some like predictions. So that's Otherwise, you have to wait and see So that sounds like, I mean, you can do this kind of.
Can I ask for a favor, please? Look in your aisle if you have any cups, plates, other things sitting around. Please pick them up, even if they aren't yours, because otherwise this place is going to get very dirty very quickly. Please do so.
Yeah, so
No need not, we didn't do the
Oh, okay. The guys are already outside.
Just take a bite. Because it is, for our method it's fine, because you just make a partition like X is on one side and the other
Thank you.
yeah, so we have to
I mean, so, the other ones don't have it.